So dear students, in today's lecture, we will discuss certain numericals related to the transformers. So basically the focus will be on the numericals related to the EMF equation of the transformer and the transformation ratio. So let us start with the numerical number one. So the statement of this numerical is a 40 kilovolt ampere single phase transformer has 400 turns on the primary and 100 turns on the secondary. The primary is connected to 2000 volt 50 hertz supply. We have to calculate the secondary voltage on open circuit, the current flowing through the two windings on full load, and the maximum value of flux. So let us solve this numerical. Now in this particular numerical, if you have noticed, so let us draw the diagram first of all. So there is a transformer. So let us assume that this is a core type transformer. There are two windings. This is the primary winding which has certain voltage source, and this is a single phase 50 hertz supply, and then we have a secondary winding also, right? Now the number of turns at the primary are 400 and the number of turns at the secondary are 100, right? So now let us write what all parameters are given. The given parameters are the power of the transformer, which is 40 kilovolt ampere. So the power of the transformer is always measured in volt amperes, and it is always assumed that the power at the input and the power at the output will always remain same. These two powers are same, right? Now the second thing is given the number of turns at the primary, let us say N1. N1 is for the primary. So it is 400 turns. Number of turns at secondary are 100. So the voltage is this one V1. The voltage connected is 2000 volts, and it is the frequency is 50 hertz, right? So the first thing that we need to calculate is the secondary voltage on open circuit. This means that the secondary of the transformer is open. This is the secondary winding and this is the primary winding. So the primary winding is the one where supply is connected and secondary winding is the one where load is connected. So that means there is no load connected as of now. So we need to calculate the voltage on the open circuit. So let us assume that the voltage on the open circuit is V2. So let V2 is the voltage on the open secondary, right? So secondary here is used for the secondary winding, and always remember that V2 or E2 or V1, E1, I1, I2, all these are the RMS values until unless specified. Until we specify a specific value or some special value, we have to assume the capital notations as the RMS values of all the relevant parameters of the transformer, right? So now here the voltage induced at the secondary winding is E2. So E2 is the RMS value of the voltage induced at secondary winding due to mutual induction, right? Now in this case these two are same. So now let us assume that these two voltages are same. E2 is equal to V2, or you can write V2 is equal to E2. So similarly, we will also assume that if E1 is the voltage induced at this primary winding because of self-induction, so this is the induced voltage at primary due to self induction, right? So and the voltage applied here is V1. So V1 is given to us, this is 2000 volts, so it is equal to E1. So these voltages are same, right? So now we have to find out the secondary voltage, that is we have to find out V2 now. So we can use the voltage to turn ratio to find out this particular value, because the value of the two windings number of turns are given, voltage V1 is given, so it would be easy for us to find out the value of E2. So we know that as per the voltage turn ratio, we know that E2 by N2, so this is for the secondary winding, is equal to E1 by N1, and this is for the primary winding, right? So now from here we can easily find out the value of E2. E2 is equal to E1 into N2 by N1. So we'll put the values here. This is 2000 volt into N2 is 100 and N1 is 400. So 100 divided by 400. So the value of E2 will be equal to, this is cancelled out. So this is, now this is equal to 500 volt. So this is the value of E2. Now because we have assumed that V2 is equal to E2, so V2 is equal to 500 volt. This is the answer for first part of the numerical. Now similarly we can find out the second part, which says that we have to find out the current flowing through the two windings of the full load. So let us draw the diagram on full load. So here is the diagram for the second part of the question, in which we have to find out the value of I1 and I2 when the transformer is connected to a full load. A full load means the rated load is connected to the transformer. So under these circumstances, some current in the secondary, which is let us say I2, and the current in primary, let us say I1, will flow at its rated value. The rated value means the value which is specified by the manufacturer, that under the full load conditions, this is the maximum or rated, or you can say rated value of the current that can flow in the two windings of the transformer, right? So now since it is the full load value of the primary current, this is let us say full load, both values of primary and secondary current, right? So the value of I1 can be calculated by using the value of power which is given, which is in kVA, divided by the voltage at the primary winding, right? Because it is always assumed in case of transformer that the power at input and the power at output, that means the kVA of the input and the kVA of the output are always same. Okay, so now, so I1 from here can be like the power is 40 kVA, which is given to us. So it is 40 into 1000 kilo because it is kVA. So 40 into 1000 divided by 2000. So 2000 is the value of V1. So it is cancelled here. So it is 20 ampere. So the value of I1 is 20 ampere. Similarly, the value of I2 can be calculated by using the formula power. So it is kVA divided by V2, because we know that the power is generally equal to V into I, and it is because measured in volt amperes, so we don't need the power factor in this particular case, right? So the power is 40 kVA, that is 40 into 1000 divided by, and the value of V2 is 500. So it is, the value of current is 80 ampere, right? So these are the values of the full load primary and secondary current. So now you can understand from here that the primary voltage is high, secondary voltage is low, but primary current is low and secondary current is high. Now this is happening because the power on both sides of the transformer is same, right? Now let us come to the third part of the numerical. So in third part of the numerical, we have to calculate the maximum value of the flux density. So let us calculate the maximum value of the flux density. Now from the EMF equation of the transformer, we have, now what is the equation? It is E is equal to 4.44 N phi M into F. So this is the peak value of the, or maximum flux, right? So phi M can be calculated. You can use any value. Let us take for the primary. Okay. So it is E1 divided by 4.44 N1F, right? So this would be 2000 divided by 4.44 into, and the number of turns at primary are 400 and the frequency is 50 hertz. So on solving this, so the answer would be approximately 0.0225 Weber, right? So this is the maximum value of flux in the core of the transformer, right? So now here you can also notice one thing, that because the number of turns at primary is greater than number of turns at secondary, so this is a step down transformer, right? Now let us take up the next numerical, and the statement is the no load ratio required in the single phase 50 hertz transformer is 6600 oblique 600 volt. If the maximum value of flux in the core is about 0.08 Weber, find the number of turns in each winding. That is, we have to find out the value of N1 and N2. So N1 is the number of turns of the primary winding and N2 is the number of turns of the secondary winding. Now in this particular numerical, this is a step down transformer. This is the case of step down transformer. Now how will we come to know whether the given transformer is step down or step up? Either we can come to know through the number of turns, or we can also know the same thing from this value. It is 6600 oblique 600 volt. So now this, the first value belongs to E1 or V1, and the second value, sorry, V1, second value belongs to E2 or V2, right? So that means this value belongs to the secondary winding or secondary voltage, and this value belongs to the primary voltage, or you can say the supply voltage, right? Okay, so now the given parameters are E1 is given, which is equal to V1, which is 6600 volt, and similarly E2 is given, which is equal to, let us say, V2, which is 600 volt. Remember one thing, this is the no load ratio. This means that our transformer is not connected to any load. The secondary is open. This is the primary winding, and the supply is connected here, AC supply. This is V1 and this is E1 here. Then we have, let us say, E2, and this is, let us say, V2, and this is open, right? So these two values are given. The value of maximum flux is also given, which is 0.08 Weber. Now we have to find out the value of N1, that is number of turns of the primary winding, and then we have to find out the value of N2, which is the number of turns of the secondary winding, right? So we can use the transformer EMF equation here, right? So transformer EMF equation is given by E is equal to 4.44 N phi MF. Okay. So let us find out. So let us take for the primary. So E1 is equal to 4.44 N1 phi M into F. So the value of F is also given, which is 50 hertz. So it is 50 hertz here, right? Now let us find out the value of N1 from here. So we have, it is equal to E1 divided by 4.44 phi MF. So E1 is 6600 volt. 4.44 into phi M is 0.08 Weber, and the frequency is 50 hertz. So on calculating the value of N1, it is equal to, so this is equal to 372. So the number of turns in the primary winding is 372. Now we can also find out the value of N2 either by using the same formula, or we can use the volt to turn ratio here, which is also known as transformation ratio, right? So it is E2 by N2, it is equal to E1 by N1. So we have to find out N2 here. So N2 is equal to E2 by E1 into N1. So E2 is given, which is 600 volt, divided by E1, which is 6600, and N1 we have calculated as 372. So let us calculate this value. So the value of N2 will be equal to 34. So this is how we can calculate the required parameters in case of transformer. So in these two numericals, we have made the use of two equations. One is the EMF equation of the transformer, and then we have also made use of the transformation ratio of the transformer, right? Now let us take the third numerical of this lecture. In this, we are given a single phase transformer which is connected to a 230 volt 50 hertz supply. The net cross sectional area of this, the core of the transformer, is 60 centimeter square. So now we have a new parameter here, which is the cross sectional area. And the number of turns of primary is 500 and secondary is 100. We have to calculate the transformation ratio, very easy. We have to calculate the maximum value of flux density. So we need this area of cross section here, and then we have to calculate the value of induced EMF in the secondary winding. That is, we have to calculate the value of E2. E2 is the induced EMF in the secondary winding. Now, how will we calculate this one? How will we solve this particular numerical? Okay. So the transformer diagram we can draw. If you feel like drawing it, you can draw. Otherwise, it is totally up to you. But if you draw, it would be good, so that it would be easy for us to solve the numerical. So this is connected to, this is a primary side which is connected to a supply, AC supply, which is 230 volt and 50 hertz, right? And the voltage here is V1, which is 230 volt, and induced EMF is E1 at primary. Then we have the secondary winding, right? Now, so this is the secondary winding. We need to calculate the value of E2, which is not given to us. Okay, so the number of turns of the primary winding are 500 and the number of turns of the secondary winding are 100. Area of cross section of this is 60 centimeter square, right? So the given parameters are V1, which is 230 volt, frequency is given, which is 50 hertz. Then number of turns of the primary is 500, number of turns at secondary 100, area of cross section is 60 centimeters square, and then okay, all this is given to us. Now the first part is we need to calculate the transformation ratio K, right? Okay, so now the voltage to turn ratio is given by E2 by N2 is equal to E1 by N1, or we can also write it as E2 by E1, it is equal to N2 by N1, and it is equal to K, right? So we can use this particular relation here, because in case of EMF, E2 is not given to us, it is unknown parameter, E1 is only given. So here, but N2 and N1 both are given. So the value of K would be easy to calculate by using the values of the number of turns. So K is 100 divided by uh, 500, because number of turns at primary is 500 and number of turns at secondary is 100. So it is K is 1 by 5, so it is 0.2, right? So this is the value of transformation ratio here. Now the second part is we have to find out the maximum value of flux density. In the second part, we have to find out the value of Bm. So Bm is the maximum value of flux density. So Bm is equal to phi m upon A area, right? So phi m, we know that it is the maximum flux associated with the iron core, and phi m can easily be calculated by using the EMF equation of either of the windings. Now because E2 is unknown to us, so we can better use the value of the primary EMF equation, primary winding, right? So E1 is equal to 4.44 N1 phi mf. So the value of phi m will be E1 divided by 4.44 N1 f. So phi m is equal to E1 is 230 volt, because V1 is equal to 230 is equal to E1 in ideal condition. We have assumed this, right? So it is 230, and then the value 4.44 N1 is also given, which is equal to 500, and the frequency is 50. So when we calculate this, when we divide and multiply this, the value of phi m will be equal to 0.00207 Weber. Now the value of area of cross section is also given to us, which is 60 centimeters. Now area of cross section A is given as 60 centimeters square. So it is equal to 60 into 10 raised to the power minus 4 meter square. Now the value of Bm will be equal to, if we substitute both these values in this particular formula, so we have Bm is equal to 0.00207 divided by 60 into 10 raised to the power minus 4. So this is equal to approximately 0.345 Tesla. So the value of Bm is equal to 0.345 Tesla. Tesla is the unit of flux density. So this is the peak value of flux density that we need to calculate. Now the third is we have to find out the EMF induced in the secondary winding, right? So third is we have to find out the value of E2. So for this we can make use of the voltage to turn ratio. So it is E2 by N2 is equal to E1 by N1. So E2 is equal to E1 N2 by N1. So this is E1 is 230, N2 is 100, N1 is 500. So E2 is equal to 230 into, so it is 230 into 0.2. So it is E2 is equal to 46 volts. So this is how we can calculate. So we have simply there is simple. These are the simple questions, formula based questions, and you simply have to understand what parameters are required to be calculated and what parameters are given, which particular formula can be used in this, in a particular question. So it would make very easy for you to understand the numerical and solve it accordingly. Now, similarly, in the last question also, the statement is very simple. We have 3300 by 300 volt single phase 300 kilovolt ampere transformer, which has 1100 primary turns. We have to calculate the transformation ratio. We have to calculate the number of turns in the secondary winding. Let us say this is N2 and transformation ratio is K, for example, and we have to calculate the voltage per turn ratio. That is, either we can calculate E1 by N1 or E2 by N2. Both are same because these two are equal. These two turn ratios are equal. We have seen this in the EMF equation of the transformer in that particular lecture. So let us see how to solve this particular numerical. So first of all, we'll write what all parameters are given to us. The primary winding voltage V1 is given, which is equal to, let us say, E1. So this is equal to 3300 volt. As you can see here, this is a step down transformer, right? Because the voltage at secondary is 300 and voltage at primary is 3300. So V2 is also given, which is equal to E2. So it is equal to 300 volt here. and the power is also given, which is 300 kilovolt ampere, right? Number of turns at the primary are given, it is 1100. So the first we have to calculate the transformation ratio. K. So the transformation ratio K is given by E2 by E1 is equal to N2 by N1. So since N2 is not known to us, so we'll make use of this particular part of the equation. So K is equal to E2. E2 is 300 divided by 3300. So K is equal to 1 by 11. And the fractional value will be, so this is equal to 0.091 approximately. So the second part of the numerical is we have to find out the secondary terms, right? And 2 we have to calculate. So we can make use of the voltage to turn ratio or this particular concept also, that E2 by N2 is equal to E1 by N1. So from here we can find out N2, which is equal to E2 by E1 into N1. E2 is 300 and E1 is 3300 and N1 is 1100, right? So it is cancelled 300. So N2 is equal to 100. Number of turns at the secondary is N2, which is equal to 100. Now the third is we have to find out the voltage to turn ratio. So we can use simple formula E1 by N1 or we can use E2 by N2. It is very simple. So by using this, let us use E1 by N1, which is voltage to turn ratio. It is 3300 divided by 1100. So it is equal to 3. Even if you use E2 by N2, so E2 is, the value of E2 is 300 and N2 is 100. So even then this is also equal to 3. So the voltage to turn ratio is 3. So now, so these were some few examples of the numericals related to the transformer, EMF equation and transformation ratio. So I hope these numericals are clear to you. These are simple numerical which are based on formulas, simple formulas. So try to solve more such numericals on the EMF equation and the transformation ratio related to the transformer. Thank you so much.